Good evening, sir. Hello.
Good evening, sir. Good evening.
Good evening, sir. I think we can wait for a few minutes and let's see if someone else will join and then we can start.
Sure.
Okay.
Yes.
Hello. Yeah, I think we can start now. So, good evening. Welcome to the third online tutorial session of the NPTEL course, Polymer Reaction Engineering. So, this, as we all know, this is a parallel session that is going parallel to the NPTEL course, Polymer Reaction Engineering. So, here we will discuss some of the numericals and some questions that will be helpful for you during your assignments and your examinations. So, yeah. So, I think we can start now. So yeah, I'm Rahul. I'm a PMR fellow from the Department of Physics, IIT Kharagpur. So yeah, so I am the online TA for this tutorial session. So let's start our today's class. So in this week we discuss few topics based on the morphology of polymers. In introduction, we had an introduction to reactor design. We had also some idea on the batch reactor, and we had some insights on the rate equations, kinetic equations for the unimolecular irreversible differential order reactions such as zero order and first order. So those were the topics that were discussed in this week. Now I think we can move on to numericals and some multiple choice questions. So yeah, so this is the first question. So the question is, the morphological features in a synthetic polymer are
Sorry,
usually.
that is not. I think screen is not shared.
Hello.
Yeah, sorry, I'm not seeing the screen. I think it is not shared.
Oh, I'm sorry. I'm sorry. I think please. Okay, just a second.
Yeah.
To share this. Yeah. Is it okay?
Yeah, it is
Yeah.
visible now.
Yeah. Okay. So once again, welcome to the third online tutorial session. Just a second. Yeah. Okay. As we said, so this is our first question for today's class. So the morphological features in a synthetic polymer are usually within our control. We can create them, influence them, and shape them to our design. So this is a true or false question. Just think for a while, and we'll discuss the answer within 1 minute. Yeah. Yeah. This is the question. So the morphological features in a synthetic polymer So the main feature is it's not, we are not talking about any natural polymers. We are just talking about the synthetic polymers. So yeah, that morphological, so I'm sorry, I think the answer is already revealed. So yeah, it is actually a true statement. We can actually control the morphological features for a synthetic polymer, where a natural, where in case of a natural polymer, so yeah, definitely it is a naturally occurring. So there is a limitation in which we can control. So we need to control the, suppose we are forming honey or something. So it is difficult for us to control each and every parameter while it is being generated in the first place. So that is the, but if it is a synthetic polymer, definitely by controlling the features such as temperature, concentration, etc., we can definitely control the morphological features of the polymer. So I think this one is clear for you. Okay, if that's the case, let's move on to our next question. Yeah, so this is a bit explanation for this question. So we can tune the morphology by choosing the required monomers. We can tune the morphological features by choosing the proper polymerization conditions and choosing the proper techniques, and also choosing the composite that we are actually choosing in order to form this polymer, or in order to induce this polymerization in the first place. So yeah, in the synthetic, it is we are able to control the parameters to a very good extent. Okay, if that is the case, let's move on to the next question. The crystalline transition temperature. So as you all know, in this we are basically dealing with the morphology of the polymer itself. So morphology, we mainly talk about how crystalline the polymer can be. Is it can it be amorphous? Can it be semi-crystalline, crystalline? So here sir has taught us about all those parameters, how things are changing. So this is a question related to the crystalline transition. So the crystalline transition temperature of a polymer is obtained when the polymer is cooled and the translational, rotational, vibration energies are decreased. And this is the first option. So you can see the polymer is cooled and these energies are decreased. The second one is the polymer is cooled and the energies are increased. And the third question is when the polymer is cooled and transition energies are remain unchanged. Okay. And the last one is that when the polymer is heated and the energy is increased. So these are the four options. We have the two parameters that basically we are talking here is are about the temperature at which we are taking the polymer to, and the other one is the what happens to the energy of the molecules within the polymer. Okay, so the first one is when the polymer is cooled and the corresponding energies of the molecules are decreased and are decreased. Okay, and the second one is the polymer is again it is cooled and here the energies are increased. Here we are talking about the when the polymer is cooled and the energies are kept unchanged, and the last option is we heat the polymer and then the corresponding energies are also increased. So which one could actually create a crystalline transition in a polymer? Okay, so there will be a formation of crystalline domains within the polymer network. So
The
think
likely option one, where we cool the polymer and the energies are reduced to close to zero.
yes. Yes, so that's the answer. So the basically yes, definitely when the polymer is well cooled, obviously the energies that is being given to the polymers will also increase. That will make the system more stable, or in the sense the molecules will more become will come to much lesser energy, and hence they can club together and form a more dense form structure that actually causes a crystalline nature in the polymer. So, yeah, as sir said, the answer is option A. The polymer is cooled and the translation, rotation, and vibration energies are decreased. So that is the answer for this question. I hope this one is clear. That's the case. Let's move on to the next question. The three polymer morphologies can be crystalline, semi-crystalline, amorphous, all of the above. So which are the possible three, or is it any other than of any other morphologies than this? So is it crystalline, semi-crystalline, amorphous, or all of the above? Some of these questions are actually taken from the previous year NPTEL. That's the same course that was run on the last year. So some of these questions was provided as assignment question for the last NPTEL course for that. So some of these questions, so you can see what kind of question that would be possibly asked for your assignment questions also. Okay, yeah, which of
It should be all three.
yeah,
Like it should have crystalline amorphous as well as it can
yes.
contain this all the three domains.
Very good. So that's the answer. So basically, according to the crystallization happening to the polymer itself, and that depends on a wide variety of parameters, including the polymer, the temperature, and the other external parameters which it is being exposed to. And depending on the many parameters, the polymer can be crystalline, can be semi-crystalline, and amorphous, and it can also be a combination of all these three together. Suppose I can show you an example here. So this is an example for PVA. So this is an XRD image of a PVA where there is intensity in the arbitrary units along the y-axis, and this is the 2 theta. So we can see that, so the one with the noise, the blue one, it is the experimental data. So this one is our experimental data. The experimental data contains basically an amorphous part, a crystalline part, and a semi-crystalline part. Okay, so there are multiple peaks that is now. So basically, see, you can see there are here we have shown two amorphous peak. One is coming at around 40 degrees, and we are also having another amorphous that phase that is happening coming around, we can say around 2025, and there is a sharp peak, comparatively sharp peak that is coming around 20 degrees. Okay, so this is an example. So this is the research paper which I got this information from. So they have created a PVA and they have studied it used as an electrolyte. So in this they have tested it. They have done a XRD analysis, and this is a very good data which clearly shows uh, the contribution of this amorphous, crystalline, and semi-crystalline contribution to um, the polymer itself. Okay, I hope that is clear. Let's move on to our next question. So the next question is it's regarding the reactor. So which of the following statement is incorrect regarding the contraction pattern of the flowing fluids in a reactor? The mixing of young fluid elements with old fluid elements at the end of the reactor, thus a lot of time is there for the reaction to proceed, which result in high conversion of reactants. The phenomena is termed as early mixing. So this is basically basically giving an definition for this early mixing. And the second one, the mixing of a fluid at the exit of a reactor, thus no time is there for the reaction of the reactants, which result in lesser conversion of the reactor. Hence, the phenomenon is called late mixing. The clumsiness and the state of aggregation is the part of contacting pattern in the liquid gas or gas liquid system. Early mixing is most effective for single flowing liquids than to entering reactant stream. So these are the statement, and what and which of the following is the incorrect statement, or which is giving you an incorrect definition for the definite terms like early mixing, late mixing, etc. Think this for a while, then we'll discuss the answer.
It should be like this the two fluids when we are having two different stream. It is better to have good early mixing
Yeah,
than a single fluid. So the last one is incorrect.
yeah. Okay. Any other answer? Any other answer? Okay, if that's the case, yeah, what I said is correct. As yeah, definitely, as early mixing is most effective for single flowing fluids than two entering reactant stream. So definitely that is the answer. So now let's move on to our next question. The rate of reaction is a function of which of the following parameters? Reacting material, temperature, concentration, type of reactor used. Which one is more dependent? So yeah, definitely we can say one or the other. So even though if you are thinking about the priority, like which one and the possibility of which one has higher can be considered as a better function as a which controls the rate of a reaction. So which of the following parameter can be considered as the uh, consider which one basically affect the rate of a reaction. Is it the reacting material itself? Is it the temperature, concentration, type of the reactor used? Which one control the rate of the reaction?
So primarily, though like temperature is also a factor, but the concentration the concentration of the reactants will be the first likely. Of course, type of reactor also is there, batch, semi-batch, and continuous, but the rate primarily depends on the concentration of the uh, reactant.
Yeah, there can be multiple parameters. Basically, what this question gives you is that mostly everything actually depends on the actually defines or determines the rate of the reaction. But
Exactly.
still,
Yeah.
yeah, if as Sir said, definitely the concentration plays a very crucial part, as though as the temperature too, and also the type of the reaction, also the reacting material. But the answer can be given as reacting material. Yes, reacting material defines the reaction, but when we consider uh, as a parameters as a whole, the rate of the reaction is majorly uh, considered by it can be temperature. Yes, as temperature increases, the rate of the reaction also increases to an extent, but everything has its own limit over which it will degrade the entire reaction. Then it is the concentration. Concentration also has this problem. If the concentration of the reactants increase or increase beyond a point, then that will lead to high density of the reactants within the chemical mixture, and that will also slow down the reaction. So everything has this uh, limit, and beyond it, it is not feasible. And also the type of the reactor, because as you can see, the type of the reactor that we use will determine like how the heat transfer happens and how much area this reaction is occurring. So that all will determine the reaction. And when we come to reacting materials, yeah, it definitely determines the products. As I say, it will defines the what kind of product. But when we see the reaction, so definitely in order for a reaction to happen, a certain reactive material should be used, and definitely it will also affect the, suppose we can choose, we can get a product out of two different, we can get the same product C from a reaction between A and B, maybe as well of A and D. Okay, so definitely material will also play a crucial role, but when we fix the material, then majorly the other three components are the major contributing factors, and reacting material, once it is determined, there is not much to do after that. Once the reaction is fixed, suppose we fix the reaction where we get A plus B, which gives C. Suppose we fix A and B, and then there is nothing more we can do with A and B. The materials are itself fixed, and the next thing what controls the reaction is basically the temperature, concentration, the type of the reactor. Okay, I hope this one is clear for you. Okay, if that's the
Yeah.
case,
Yeah. But
when we
it is
come,
answer is three.
yeah, answer is three. Basically,
Okay.
it can be four, but uh, comparing to the other three, A is bit obvious, and it is the major controlling factor parameters of a reaction is the temperature, concentration, and the type of the reactor. So
Exactly.
basically,
Yeah.
the major answer is
Clear.
three.
Clear.
Good. Okay, so this is the next question. Which of the following variables affect the rate of a reaction? Temperature, composition, pressure, all of the above. This is
It
also
is
very similar
all
question.
of
I
them.
think, yeah, I think this is from the previous year question paper. So, yeah, which of the following actually affect the uh, reaction rate? Temperature, composition, pressure, all of the above.
Yeah, it is all of the above.
Yeah, okay. So, yeah, that's a obvious question. So it is all of the above. As we said in the previous question, definitely temperature and composition plays a crucial part, and also the pressure. For example, there are reactions like not specifically for maybe for polymers, but still we use the techniques called hydrothermal reactions, where we keep the materials in a closed chamber, very closed chamber, and we keep the volume. We keep it in a very closed chamber such that there is no leakage of air or any such thing happening, and we keep the reactants in this material, and then we keep the entire thing inside an oven. So, and then we heat into our desired temperature, maybe 200 degree or whatever we need. We increase the temperature, and thus we give two things to the material. We expose the material to both temperature and as well as pressure. Okay, so we increase the temperature and we increase the pressure, and thus this will uh, induce certain kind of reaction, and that will give us a desired products. Okay, and there are certain reactions which can happen only under this condition, or which will happen best under this condition. For example, mm, consider reaction of, so I'm going a bit off topic, and still consider a topic like where we usually etch the mexines. Mexine is a class of material which is basically uh, we have a max phase. Max phase is where we have a metal, aluminum is linked, and we have a functional group which is basically chlorine or fluorine basically attached to it. And we, in order to convert this max phase would be much compressed layers. Suppose we want to convert this max phase into mexine, which is more freely standing, much more loose and filling. So the distance between the layers would be drastically increased once we go from max phase to mixing. So in these kinds of reaction, we can do in both ways. One way to we can keep this in hydrofluoric HF acid and leave it in a stirring condition for about 1 week or 5 days, depending on the literature. There are people doing it in different way, but also we can do so better result. We get better, but this is one way, but we can get better result when we do this in particular hydrothermal method. So that is one. So there are reactions that particularly depend on pressure that we are applying on the, so that it forms our uh, desired output. Okay, so if that is the case, yes, as Sir said, the answer is all of the above. Temperature, composition, and pressure, all of this will contribute to the rate of a reaction. Okay, so if that is the case, let's move on to our next question. Yeah, so this is a much more an explanation for the same question. So what actually happens can be seen from here. So as the temperature increases, the number of successful collisions that overcome the activation energy barrier will increase, and thus the reaction rate will also increase. When we come to the composition, which is also the concentration, the more reactant molecules per unit volume means the more frequent collisions between the molecules, thus increasing the number of opportunities for a reaction to happen, and thus it speed up the entire reaction. And lastly, for pressure, it's said for gases, but I don't think it is not just for gases, it is a common thing. So here also, when we increase the reaction, I said that the reacting molecules, the frequent collisions will definitely increases, and thus that will lead to much more higher chance of reaction. Thus, it will speed up the entire reaction itself. Okay, if that is
Yeah.
okay, let's move on to the next question. So, which of the following statement are correct for a non-elementary reaction system? So, we talked about elementary reaction system and non-elementary reaction system. So, which one is correct for a non-elementary reaction system? There is no direct relationship between the rate equation and the stoichiometry of a reactant involved in a reaction medium. That's the first statement. There are needs of a series of elementary reactions to solve a non-elementary reaction system. Third one is we have to assume a series of elementary reaction occurring with a negligible amount of intermediate product are formed for a short time period. The fourth one is the stoichiometric coefficients are same as the power raised to the corresponding reactant concentration terms used in the rate law. Then the reaction is said to be non-elementary reaction. So basically here also we are talking, we need a proper definition for this non-elementary reaction system. So which one suits the best for a non-elementary reaction system? Think for a while. Then we will discuss the answer. Think all these were discussed on the second lecture, if I remember it correctly.
I think actually for me it was like since I am having the other session,
Mhm.
I could go through like almost first fully and second is now today it is going on.
Okay.
probably I may have to go through fully to
Okay.
explain.
Yeah. Okay. There is another attendee also. If uh, so, if, yeah. So I clearly explains about what are these elementary and non-elementary reactions. So he'll explain you better. So all the explanations are properly given in the lectures itself. Okay. Um,
Yeah.
yeah. So then I'll discuss the answer. So basically, all the first three comes under the non-elementary reaction. So basically, it says that there is no direct relationship between the rate equation and the stoichiometry of the reactants involved in the reaction medium. So that is one of the properties of this non-elementary reaction. The stoichiometry of the reactants does not have a direct relationship on the rate, and there are needs of a there are needs of a series of elementary reaction to solve a non-elementary reaction. So it is not a one-step process. There are a series of elementary reaction that should be uh, done in order to form a non-elementary reaction. Name itself shows it is not an elementary reaction. It's a non-elementary. So there should be multiple, just not just one, multiple reactions should happen. So that is also a proper answer. And the last one is we have to assume a series of elementary reaction. Yeah, this is similar to our previous thing, but the major difference is that reactions occurring with a negligible amount of intermediate products and are formed for a short time period. So here we are talking about the formation of intermediate products, and those intermediate products does not actually affect our whole reaction, such that they become dominant and or they react with the entire reaction and gives us some other um, result. So but it is like these are it will just produce only a negligible amount of intermediate products, and that will be produced only for a short period of the entire reaction itself. So these are the three possible answers. Yeah. So this is a bit much more explanation. I think I have already explained the thing. Yeah. So let's move on to the next question. Which are correct for molecularity of a polymer? It can be fractional. It can not be a fractional. The molecularity is only used for the elementary reaction. The molecularity is used for the non-elementary reaction. So it talks about the molecularity, how the molecularity actually affects the polymerization. So just think for a while, then we'll discuss that. So I hope you have understood what is meant by molecularity. Molecularity basically means the reactants, basically the number of reactants that is participating in the reaction. So yeah, so that is molecularity. Now just think around the answer. I hope you will be able to give some answer.
So one is that it can't be fractional.
Yeah,
Means like it should be okay. It should, at least two molecules, one a single molecule or two molecules. Minimum one or two molecules are required, so the fraction is not there.
yeah, that is very good guess.
And elementary, okay, option C and D, I have doubt because since I have not gone through, maybe it will be better I will hear from you.
Yeah. Yeah, then I think we can discuss the answer now. So molecularity is basically considered when we have a non-binary, non-elementary reaction, because in non-elementary reaction there will be the series of reaction that will be happening parallelly. So whereas in elementary reaction it is just A and B producing C. So in that case molecularity, uh, yeah, it is it is much more a wider sense of answer. Like molecularity is not only used for reaction. So it is basically used for all the systems, and as I said, it can be a fraction also. So it is used in elementary reaction as well as non-elementary. So it is basically used in all the reactions. So that is the answer. The
Clear.
next, yeah. So basically, the justification for these statements are molecular one. The model, yeah, as I said, this is the definition of the molecularity. It is defined as the number of molecules of chemical species that are involved in a chemical reaction. It is always a whole number because it represents the stoichiometric coefficients, the balanced chemical equation for a elementary reaction. So this statement is okay. Yeah, the second statement can be fractional. That is incorrect. Yeah, basically these are the other. So if the reaction is heterogeneous in nature, then only heat transfer becomes important factor that affect the rate of reaction. Only mass transfer become important factor that affects the rate of reaction. The rate of heat and mass transfer become important factor that affects the rate of reaction. Neither heat or mass transfer is affected by the rate of reaction. So which one is affected? So first option it says about the heat transfer that will become an important factor. Second one talks about the mass transfer. It says that mass transfer is an important parameter or important factor that happen that affects the rate of the reaction. The third one is both heat and mass transfer actually affect the rate of the reaction. The fourth one, neither heat or mass transfer actually affect the uh, rate of the reaction.
It should be like both should have an impact. Like both heat and mass transfer option C for will affect the rate of the reaction. Both heat and mass transfer effect, especially for heterogeneous.
Yeah. Yes. So yeah, as I said, both. So this is also very fundamental question. So the both rate of heat and mass transfer become important parameter. But yeah, definitely, if a reaction has to happen, there should be an optimum amount of heat transfer and there should be an optimum amount of mass transfer that is happening with the reactants and the products. So hence, that is the best answer. Okay. Yeah. So this is the justification for this. I think it is a very straightforward question. So let's move on to the next question. So the glass transition temperature of a polymer can be determined by which of the following instrument? AFM, FTIR, AFM, TEM, which is atomic force microscopy, it's actually transmission. There's some spelling mistake. Uh, so transmission electron microscopy, Fourier transform, infrared spectroscopy, differential scanning, calorimetry. So which of the
Here, AFM and TEM both are for surface morphology characterization, and FTR anyway that gives the functional backbone.
yeah
DSC is the one which gives the TG or TM, whatever the transitions happening in the systems.
yeah so basically in among this the one that is majorly depending on the temperature also it is basically calorimetry where we measure something as a function of temperature. So basically so it is the DSC that actually controls the I mean, not controls that will also actually help us to see the glass transition temperature not only in polymers but in basically mostly all the materials. So the glass transition temperatures are basically measured by using differential scanning calorimetry, which is also known as DSC. Okay, so if that's answer, so that is basically we use atomic force microscopy to see how the basically we need to know the thickness or how the protrusions are happening in the materials. It basically gives a length or height profile of the materials. In here, it also gives us a basic structural morphology, basically in a three-dimensional. So basically, suppose if I'm having a material that is hollow inside, so we may not know the nature by just having a scanning electron microscopy or SEM. SEM would give us an it is just like an our photograph, and TM is like an X-ray. We can say it will give us an information how the things are happening inside the material. Like it will give a three-dimensional, or we'll get an information within the bulk of the system, whereas SEM would give us a surface uh, morphology of the system. FTIR, which is the Fourier transform infrared spectroscopy, this technique will give us information about the functional groups that are present in the material. Suppose some material having a OH group, or it having a COOH group that is attached to it. Suppose we are having a graphene oxide. So we are having graphene and it is attached with multiple other functional groups, majorly oxides and other OH groups and etc. So that would we can know how much it is graphene. Then later when we calcinate it, we can get the we can take the graphene oxide, which is GO, to reduce graphene oxide where the number of these functional groups are reduced. So all this information can be analyzed through an FTIR pattern. And the other one is differential scanning calorimetry, where it is basically a temperature study of the material, which will give us the information how the temperature is affecting the your material, how stable is your material. All this information can be understood by using a differential scanning calorimetry analysis. Okay, if that is clear, let's move on to our next question. So this is a typical DSC thermogram, and there are different points marked in this. So this is a very typical DAC diagram that one can see. So there are 4 points marked, which is A, B, C, and D. Try to understand this figure, and then we will try to know what are these points A, B, and A, B, C, and D corresponds to. So this is like the output that is generated from a DAC, or the graph that is being generated from a DAC is basically called DAC thermogram. Just like we say, SEM um, SEM is actually diffractogram when we generally say it as an image, but basically SEM should be called as a diffractogram. And as well as XRD also, we are saying it as XRD pattern. Similarly, the result of a DAC is called a thermogram. And yeah, so there are 4 points marks somewhere around here. It is called A. Somewhere around here it is called B. The point which here it is called C. The point here it is called the D. So there are 4 typical points one can observe from a DAC. So what are these? A, B, C, and D. Okay, all right.
Likely, the blast transition temperature should be A.
Yes.
D is a melting transition.
Yeah.
These two and clear, but out of B and C, one is for crystallization. That is, I think it should be B. Uh,
Yeah. These
C,
points can be relative also, like how we define the point.
correct, correct.
Yeah,
That
I can say this is the onset of glass transition temperature. This is the onset of crystallinity. This is the onset of molten state, and this is the onset of complete degradation. So, yeah, basically, what Sir said is absolutely right. So, yeah, so if that's it, let's discuss the answer in a proper note. So this actually uh, corresponds to the glass transition temperature, and this actually represent the crystallization temperature, and this actually starts. Basically, we can say these are the onset. So this actually starts the melting temperature, and this is the degradation temperature where the basically the material is lost. The material that you start with will be completely lost, and it will be something else after that particular temperature. Okay, so we can see this is a comparatively very high temperature compared to other. Okay, okay,
yeah, yeah.
yeah, okay. If that is again, let's move on to our next question. So, what are first order and second order phase transitions? So, phase transitions are things are kind of transition that will be discussed in wide variety of areas, starting from physics to chemistry, multiple material science, and mostly starting from magnetism to um, basically in all the field we can thermodynamics in mostly everywhere we can actually talk about the phase transition where one form of a material or one form of say uh, it can be particles or anything, one form is the one form is getting changed to some other form, and it can be classified as first order and second order. So can you please just define what is first order and second order phase transition?
Likely, first order doesn't involve any phase change. Phase means direct change may not be there or within this change. Whereas second order phase transition, generally that involves something like melting and or sublimation, boiling, something like that, where the phase change is also involved, if I am correct.
I think the observable changes are happening in the first order. Observable changes. So I think if it is melting, so if you're talking from the basically from the physics point of view, I'm not that much aware of it from the chemistry point of view. So basically, from first order transition would bring the observational changes as far as I remember, and the second order will correspond to some other changes that is happening within the system. So we can discuss on that.
Yeah, yeah,
Yeah.
maybe wrong.
Yeah. So this is the major thing. So major change that one can observe from a first order and second order transformation is the continuity. So there will be an abrupt change in certain parameters, whatever it can be. Suppose we are observing magnetism with temperature, or if we are measuring capacitance with temperature, so there can be multiple phase transitions happening. So if I'm talking from physics point of view, but this is similar for the other cases also. So there is an abrupt change that is happening, so that is a typical characteristic of first transition. And the second one is it involves latent heat. The heat is absorbed or released at the transition temperature, maintaining a constant temperature for some time. So if we measure for, yeah, so you can see from the figure also, here we can see that the temperature will actually remain constant, and here the solid is actually melting. So there is a phase transition happening at this particular point, and see here the latent heat or the basically the heat absorbed is actually constant. So the heat that is being absorbed or released of that is not changing. It is happening at a particular heat point itself, and but the heat that is used is entirely used for the change in its phase. Okay, so that is the phase transition happening, and it is the one of the major C. So if we have a random graph that is given to identify between first order and second order, the first thing we need to look is the how how continuous is the graph. You can see from this it is fairly continuous. Still we are having a sharp point, but still if you are when we look at this point here, it is changing from one point to another, and we are having a sharp change that is happening within the system. So that is the major point of the first order research. The second, and also as I said, the visible change, like as you said, that comes actually under the melting, crystallization, or glass transition. Everything comes under first order phase transition, and in the second order phase transition, it is actually continuous. So there is a gradual change. Here it's an abrupt change. Here is in second order there's a gradual change. So here it is moving from glassy to rubbery state. So from at point Tg, so there is a phase transition happening that corresponds to. Okay, so there is some mistake here. Yeah, the option here there is a mistake. So that is actually for second order transition, and it is gradual, and there is no latent heat that is here, and visible changes are also lesser in case of second order phase transition. Okay.
So just one small doubt here,
Yeah,
like
please.
glass transition, whether we should consider as first order or second order?
Yeah, glass transition, I think it is second order, sir.
Exactly, yeah,
Yeah.
because there is no phase change, melting, crystallization, sublimation, yeah, all these things we can.
Yes. So I think it is for second order, sir.
Yeah, clear, clear. Okay.
Yeah. So let's move on to our next question. So the effect of macromolecules regularity on the crystallinity can be seen in case of dash and dash configuration. So I think I already given you the answer also. It's basically cis and transfer. So basically, so yeah, I forgot to keep this as a animation. So yeah, sorry for that. So I didn't give an option for just thinking. So basically, we can see not for all, but there are molecules that shows um crystalline crystallinity in both its cis and trans form. So this you can see this from the study pattern. We can see sharp peaks which corresponds to that of crystals. So both cis and trans configurations of molecules uh, can form crystallinity. Okay, it is not that if a molecule is showing crystallinity in its cis form, it doesn't mean that it won't show that in its transform. So it can show even if mm, the chirality changes, still the crystallization of the polymer would remain intact. So that is a typical example. So this is an example for a cis and trans molecule that is showing its crystallization even it's in its cis and trans form. So this is also a research work that I took from the chemical physical chemistry physical. So yeah.
No, just to clarify whether we are the answer is we are looking only for azobenzone type
No.
because
Yeah, we are just talking in a more general form. So, yeah, I think this question
more
should also have an introductory matlab, we also we should have given some kind of introductory part to this question. The major idea of this question is that the molecule can it does not depend on its cis and trans. The molecule can show its crystallinity even on both cis and trans formations.
okay, because the natural rubber and Kutta Darsha, if we see, natural rubber has this configuration and
Yeah,
the other one is of trans.
yeah,
So Kutta
that's
Darsha is having more crystallinity because of trans configuration, but here we are telling that that is also not a criteria,
that is
even
not a
both.
yeah that is the thing that is
Okay,
not a basic that is not a I mean that is not any fundamental thing that is applicable for every. So this is a typical example where cis and trans both shows crystallinity.
okay. Clear, yeah.
Yeah, so that yeah, so that is not a general case. So which of the following statements are incorrect? Crystalline grows at nuclei and crystallites grow by addition of molecules throughout a supercooled liquid. The crystallization of a large material on a single nucleus result in the formation of single crystal. The size of a crystalline grain is independent on the concentration of the nucleating centers. The crystalline grain plays an important role in the properties of polymers as they are lines of weakness and discontinuity. Think on the statements for a while and then we discuss the answer.
I think it should be the C. The size of crystalline grain is dependent on the concentration. It is not independent.
Yeah, definitely that is a good one. Okay, so if that is clear, we can discuss the statements one by one. The first statement says that the crystalline grows at nuclei and crystallites grow by addition of molecules throughout the supercooled liquid. Yes, that is the case. For crystallization to happen, there should be nucleating point, and surrounding the nucleating point, the other, it is not just for polymers, but it is true for in general case of any formation of crystals. So there will be a nucleating point, and surrounding it other particles come, and then it will form a structured arrangement, thus forming a crystalline uh, crystal. Yeah, crystal itself. The second one is the crystallization of large material on a single nuclear result in the formation of a single crystal. Yes, definitely that is the answer. So if there are multiple nucleus, it will form multiple kind of grain boundaries, and maybe it cannot. It will have a completely amorphous nature. It will be having some crystalline property at a very small scale, but when we consider as and consider bulk structure, it will show a proper crystalline nature. It will basically form an amorphous nature where we have multiple orientations of the particles. The third point is the size of the crystalline grain is independent on the concentration of the nucleating center. No, definitely it is not independent. It is dependent on the concentration because, yeah, definitely the size of the crystalline grain is dependent on the concentration of the nucleating centers. So uh, if there are more number of nucleating centers, then it means that even if suppose we are having just a second. Yeah, suppose we are having a region, and suppose we are having a single nucleating site, then all this will form a single crystal. And suppose we are having a region or area where the nucleation or the crystallization happens, and there are multiple nucleation centers, and this will corresponds to formation of multiple kinds of crystalline domains. Okay, so definitely it is not independent, and the concentration of the nucleating centers will influence the size of the crystalline grain. So here we can say this entire thing is one crystalline, one grain, crystalline grain. Whereas if we consider here, the crystalline grain is only this much. So definitely the concentration of nucleating centers will influence the size of crystalline grain that is produced. The third option is crystalline grain play an important role in the properties of polymers as they weak as the lines of as they are the lines of weakest and discontinuity. Definitely, if it is one big crystal, then definitely the mechanical properties would be much better if we are just talking about the mechanical properties itself. Whereas if you are having a polymer which is having multiple crystalline grains. So the whole polymer is can be considered as different compression, different um, crystallines with different grains. Then that will definitely affect the entire mechanical strength of the, not only mechanical strength and other parameters also of the polymer itself, and that will definitely, it's not an uh, interesting parameter that we look upon when we think on the mechanical strength of the polymer. Okay, if that is the case, let's move on to our next question. It is, what is a polymer spherulite? Think for a while, then we'll discuss this. What is polymer spherulite?
It is like a polymer starting from a single point and start growing in a multiple, maybe in a same polymer, like it starts in a like a chain, uninterrupted chain in multiple directions. And together, when we see as an overall crystallite, it looks as a spherical system, but it grows in a multiple direction, like multiple direction in the sense maybe a center point. From there it goes like a different chains, and one chain will not have an interaction with the other chain, so independently all will go grow,
Mhm.
and together it gives the shape of a spirulite.
Yeah. So yeah, that is the thing, and also there is also this idea of crystallinity and amorphous regions within. So as this spread out, there will be some region where it is purely crystalline. There will be very good crystalline nature, and there are region where there are lesser. So basically, the region in between the two chains. So it will be forming chains, and the region or the region which is kind of far apart from the central line of crystallization, and that part will have more amorphous nature. So one a better or a more consistent definition is like when a molten crystallizable polymer occurs, the crystal grows from the individual nucleus and radiate out like spokes of a bicycle, and it is illustrated, yeah, in this figure. The crystalline portion actually radiate out in three dimension, forming spheres that are also called the spherulites. So here we can see there is a proper crystalline nature which is called the amella part, and there are some regions that is kind of a bit far from the center of this crystalline part, which is actually forming kind of amorphous nature, and it is called a amorphous region. Okay, so as I said, that is the answer. When a crystallizable polymer, not all polymers can show this property. When a crystallizable polymer, actually, when it polymerize, it will actually start polymerization from one point, one center point, and then it radiate outwards, and it will radiate outward, forming crystalline nature, and not and the entire thing won't be in crystalline nature. So there are regions which are amorphous in nature also. That is the major idea of this spherulite. That is that question. Let's move on to next question. So, so this is a typical structure of a spherulite, and there are 4 points marks. So please try to identify these 4 points: A, B, C, and D.
So A, likely it is like a lamellar structure within the spherulite, and B is more of, that is okay, A is more of like you can say crystalline part of it, and B is amorphous where all are mixing together, not in an ordered way.
Yeah,
Say D, likely it may be a tight molecules which has the interface, like it is between both the laminas.
yeah. If that is the case, then let's discuss the answer much more proper. So basically, as you can see, this one in the lambda, basically that you can see there is a much better proper arrangement of polymer here. So it is the crystalline lamella. Lamella is basically the region. We are talking about the region, the single part. So we are taking a single strand, and hence we are talking about this lamella thing. So this basically is a lamella, and the here we can see it is much more randomly oriented. So there is no proper orientation itself. So it is called amorphous lamella. And this part we can see if we take a closer look of this particular region, this part is called the, so this exact thing is called the folded chain, and the one where we can see this orange thing is called the molecule chain. So these are the, if we even go further into the structure of the spherulite, we can see basically all these 4 structures.
This the last two, just folded chain and molecular chain, I'm hearing for the first time. Like it will be like
Crystalline
uh,
itself, but we are just focusing more and seeing. So even if it is forming a crystalline region, there will be an uh, amorphous thing that is going running in between. So we are focusing on that, and this particular that is showing this entire crystalline nature, that is called the folded chain, and the chains that the amorphous chains that are running in between this uh, crystalline part is called the molecule chain.
okay, okay,
Yeah,
clear.
we can get a better understanding from this lecture also.
Yeah.
So now this, okay, I already give you the answer also here. Forgot to keep it in the. So basically, everyone from a chemistry background will definitely know what is Arrhenius equation, and basically Arrhenius equation is will help us to understand about the rate of a reaction, how will the reaction will actually happen, and yeah, yeah, the basic the equation would link between the the basic equation will be like k, or maybe r is equal to some k into e to the power minus ea by rt, where ea is the activation energy. Mm, yeah, and r and t we all know. R is the real gas constant, and t is the temperature, and t is the constant, and r is the rate. So this is the thing. This is the equation that will be not only just a chemical reaction, but in general, if anything that has to be happened, that will happen as a function of time, and that will peak at a particular temperature. If anything that has such kind of a nature, then it can, these equations can be used in those particular cases. So here yeah, Arrhenius equation that is used in many aspects. Even if you're talking in terms of capacitors, there are theories of capacitors that will actually use Arrhenius theory to differentiate between the forms of capacitors that is actually being caused. So it is used in multiple areas of science. So here, uh, yeah. So when we plot a graph, typically represent the Arrhenius equation using this particular graph, where we plot log K, where K is the specific rate constant with 1 by T, which is 1 by temperature, and the unit is Kelvin inverse. So yeah, so this would give us uh, line with negative slope and the negative slope, and we'll discuss more on the probably in the next question and the upcoming questions. So that is the basic idea of Arrhenius slope. I think this
Clear.
is very
Yeah.
clear for everyone. Those are from a chemistry background. Definitely there will be much good understanding on the Arrhenius equation. Okay, so let's move on to the next question. It's like state rate law. So what is this rate law? It is much very similar to Arrhenius equation itself, kind of similar to Arrhenius equation itself. So here we are supposed to define this rate law.
Probably, no, I know one is with respect to burn rate law, that is uh, a constant multiplied by pressure whole power n.
Yeah, I
Uh,
think
the,
this here just we are talking about any reaction, maybe
okay,
some
sorry,
case
actually,
considering
I haven't
any.
gone through this lecture. Sorry for that.
Yeah, yeah, okay. So all this mainly many of the upcoming topics is relevant in multiple field. So if I ask one question, it can have multiple answers also depending on the field that we are talking. So here we are talking about the rate law that is uh, for a reaction that is happening from A to B at some certain parameter. Okay, so some parameter is playing in between this that is responsible for taking A to B. And what is this? How we will define a rate law for this particular case. So basically, all this is
Yeah,
related to.
yeah, just to understand, like it is chemical reaction kinetic means rate of the reaction is
Yeah,
proportional to the moles, like concentration of moles with
yeah,
respect to time.
yeah,
Then K will be the rate constant,
yeah. Yes. So
and the rate is explained in negative because
yeah,
of the concentration reduction. Okay.
yeah. That is the answer. So here also we are having a similar parameter such that of a Arrhenius equation because the reaction itself would peak at say some particular energy. So at particular energy we can see that the rate of the reaction would be at its maximum, and later the reaction may becomes much more weaker. So as I said, there is a negative sign there, which is responsible because the uh, concentration or the concentration of the particles, say here we are talking about particle A, would be decreased as the reaction proceeds. So that is the reason we are having a negative sign here. And yeah, so this is the temperature dependent term. Ca is the concentration of reactants A, and N is the order of chemical reaction. Okay, if that is clear, let's move on to the next question. Distinguish between A and B in the figure. So basically we are asking about the how will be the activation energy. Yeah, I should have added more into this question. This a blunt question without any much more detail. So just justify which one will have much higher activation, which reaction. So this is reaction path A and this is reaction path B. Which one has a higher activation energy? Higher activation energy.
So it should be the curve which is having more steep slope. So A likely because the activation energy is the slope of this equation.
Basically, in this kind of a graph, basically the slope is proportional to EA and it is inversely or maybe E and it is inversely proportional to temperature. The slope would be something like that. So the one which is having a higher slope corresponds to the one which is having higher activation energy, which means that reaction will happen at a higher energy. And the one with the lesser slope means it will have a lower activation energy, and it means that the the reaction can take place even at smaller temperature, smaller energy. So if we just by considering the activation energy, we can say the reaction is more probable to happen through this B path rather than A path, because the activation energy for this B path is much lesser than that of the A path. So that is a major understanding one can get from a graph like this. Okay, fine, clear? Then let's move on to the next
Yeah,
question.
clear. Yeah.
Yeah, yeah, thank you so much. So, according to collision theory, the specific rate constant can be described as k is equal to T0 e raised to minus e by RT, k is equal to uh, t raised to 1 by 2, k0 e raised to minus e by RT, k is equal to t raised to 3 by 2, k0 e raised to minus e by RT, k is equal to t square e raised to minus e by RT. Which one will actually represent an equation for k? The only difference that is happening here is depending upon the power of temperature. So is it like going like T is proportional to T, or it is like T is proportional to T power half, or it's like K is proportional to T power 1 by 2, or it's like T is proportional to K is proportional to T square. So which one can be a better answer?
This also I am yet to go through. Maybe
Yeah, yeah, these things will be discussed in the lectures. Okay, if that is case, let's not waste the time. So it is the option B, which is K is actually the reaction constant. If you derive it, so there is a proper derivation from this. So if you derive, we can see like T will be proportional to T raised to 1 by 2. Okay. So yeah, that is the answer. So what is transition state theory? So transition state, so these are also actual for the topics that would be discussed applicable in multiple fields. Basically, chemistry, even from the chemistry point of view, there are multiple chemical aspects. So the basic definition can be different, but in our case, the transition theory is like a product we are having a reaction from A to B. A is changing to B.
whether it is the equation or the theory which explains like how this activation energy varies when we start from a reactant to product, and in between there is an intermediate.
Yeah, that is that's it. So it says that suppose we are having a reaction which takes A to B. Between the reaction, there is another state where it can actually go to C, and after that it will go to B. So there is an intermediate state, and sometimes this state will be more stable. So there, so depending upon the reaction, there if we are not controlling the parameters well, there is a higher chance that A will form C instead of forming B, because there is an intermediate state that is stable. Sometimes this will be a very minor state, and the the probability, or if I say the energy of this is much higher. Suppose uh, suppose we are having this, suppose we are having energy E1 for this path, and we are having E2 in this path. Sometimes this will become very closer to that of E1, and hence there will be kind of an equal probability for A to become C as well as A to become B. But if suppose this is much larger, then probably this will form B, but there is also probability that it will form C also. So all this would hinder that we should have a good control over the reaction so that we will get our desired product. Now let us have a proper definition. So yeah, transition state theory describes a transition state that will happen between reactants and products in a chemical reaction. The specimens that are formed during the transition state are known as activated complex. So you can see from this reaction. So we are having a reaction where hydroxide ion act with CH3Br and it can form an intermediate state, and then it can form CH3OH, which is methanol, and then also bromine. So yeah, so that is the thing. So here we are having a plot which discuss about the Gibbs free energy with the reaction quantity. We can see that the formation of the so there is a high when we just consider this transition state and the product state. There's a huge difference between the Gibbs free energy. The first thing to note is that the reactants, comparing to reactants, the Gibbs free energy for the products are much lesser, but it is increasing for a particular state, and at that particular state, since there is a higher Gibbs free energy, it will always tends to not to stay in this particular region, but to move to the final state, final product state. So this is a typical example where we can illustrate the transition state theory. Okay, so yeah, this is just and this is just an explanation for this graph, and this tells us about the other names which can be given to this transition state theory. So it is also called the activated complex theory and absolute rate theory, and also it is called the theory of absolute reactions. So there are multiple names for this particular theory, and it is a very fundamental theory that one should know while discussing about chemical reactions. Okay, if that is the case, let's move on to the next question.
Yeah, yeah.
Yeah. Which one is the unit of rate constant for a second order reaction? And here we consider time to be in seconds. So it is the second inverse. Is it mole inverse, second inverse liter? Is it mole to the power minus 2, liter to the power minus 2, second inverse? Is it mole to the power minus 2, second inverse liter? So which one is the unit for rate constant?
So it should be the second one, mole inverse liters per mole per second.
Yeah, that is the answer. You can have a general form for the nth order reaction, and it can be like mole second to the power in minus 1, no, in 1 minus n times n. So when n becomes 2, it will be mole inverse, second inverse, and or yeah, it's like liter per mole, right? I think I messed up the equation. General form can be written as 1 by mole into second inverse to the power n 1 minus n, I guess. No, it's like n minus 1. Yeah, this is the case. This is a general form for an nth order reaction. So if you plug in the value, here it is said that it's a second order reaction. So if we keep n is equal to 2, then we can write the equation liter per mole to the power 2 minus 1 second inverse. So it will be basically liter by mole second inverse, and it is equal to mole inverse liter second inverse. So yeah, this is the general form. I mean, this is the general formula one can use in order to calculate the unit of rate constant. This is a very typical question that will be asked in chemistry. So yeah, this is liter by mole to the power n minus 1 to n s to the power minus 1, where n is the order of reaction. Okay.
Yeah, clear.
If that is the case, let's move on to our next question. So here, the reaction between P and Q is second order in P and first order in Q. The rate of this reaction is R. Now the concentration of P become halves and Q gets doubled. What will be the new rate? So I think this is also a very fundamental question. We will answer this one.
Probably, I think we can discuss. I was not clear, but double mind on this.
Okay.
Yes, okay, now it's yeah. Basically, now P becomes alpha. So P is already in the second order and Q is in the first order. So second order becomes half and Q gets doubled. Assumption is like it should be double, like new rate should be double. Maybe not sure.
So I can explain the answer. So basically, we can write the rate equation as R is equal to K into concentration of maybe A into concentration of B to the power N, which corresponds N and M, which corresponds to the order of reactions for N and A and B. So this is the basic equation. From this, we can easily solve for the answer. So here we can write R is equal to K into, it is said that we are having P and Q, reaction between P and Q. Q is in second order. Yeah, P and Q, where Q is in second order and P is in the first order. It says that P is in the first order and Q is in the second order. Okay. And the next thing what they say is that the rate of the reaction is
Sorry for that. It is the other way, na? Like it says relation between P
second
and
order.
Q.
Okay, I'm sorry. I'm sorry.
It is second order in
Yeah,
P
sorry,
and
sorry, sorry. Second order I made it. Q is in the source. So there should. Uh, so there is some this problem in the formation of the question. So reaction happening between P and the reaction is here it should be reaction. Reaction is second order in P and first order in Q. So it is P square and Q power 1. And the second statement says that now concentration of P becomes half and Q gets doubled. So now the but the reaction now we are having some new reaction rate which is like R itself. So here P becomes half, right? P becomes P by 2 and Q becomes 2Q. So basically it is K P by 4 multiplied 2Q. So it can be 2 times. So this will go this side. So this new R, so I can call it as some R prime. So 2R prime is K P. So it's, there's a square here for P. So it's K P square Q. So this is nothing but our initial R. So basically now new reaction, this will become half of the initial. Okay, so R was our initial thing where P and Q were in some stoichiometric. When we reduce the concentration of P to half and when we double the concentration of Q, actually the reaction rate of reaction will become half of the initial one. Okay,
yeah, it is clear. Yeah.
this is a very easy question, but it is just the concept of this rate equation. Okay, now see this reaction. Here in this reaction, we are having 2A plus 3B, which gives us 5C, is carried out in a reactor. If at a particular point the rate of disappearance of A is 10 mole per decimeter cube second inverse, mm, what are the rates of B and C? The rate of disappearance of A is given. Now we need to know the rate of reactions of or rate of disappearance of B and rate of appearance of C. This is the question. So this is the question. 2A plus 3B gives us 5C. Yeah. So we have, so this is also a typical question that will be asked in case of this reaction equations and all. I can explain the question. Suppose to start with, let's go from the basics. Suppose we are having a reaction where A becomes B. Okay, here we can write the reaction equation as d of A by dt, where the rate of change of or rate of disappearance of A is equal to rate of disappearance of B. And we give a negative sign to A because this is a decreasing thing. Okay, so this is the fundamental thing. Now, in this case, now we can move from this simple case to much more comparatively complicated case where we are having 2a plus 3b is equal to 5c. Here, the general convention to write is like these two are disappearing while this one is appearing. So we write it as minus 1 by 2 dA by dt is equal to minus 1 by 3, which is the coefficient of this reaction, which is dB by dt is equal to, it is appearing, hence it is a positive one, and this is dC by dt. Now and it is given that the rate of disappearance is 10 mole per decimeter cube second inverse. So we can get it is given by dA by dt. It is particularly given this dissipate. It is a rate of so it is already given in the minus. So dA by dt, since it is already mentioned disappear, we can write it as minus 10 more dm cube s inverse. Okay, so basically we can write it as such. We can write in a positive way. So we can write dB by dt is equal to minus 3 by 2 into dA by dt. So it will be minus 3 by 2 multiplied by 10, which is minus 15. So the rate of, if we are just talking about the rate, so it is minus 15 more decimeter cube second inverse. And similarly we can do for C, where it will be, so it is a positive thing, so we can write dC by dt will be 2 by 5 of how much dA by dt. It is nothing but 2 by 5.
So 5 by 2 or 2 by 5?
It is 2 by 5. So, no, no, I mean, sorry, it's 5 by 2. It will
2.
change
5
the
by 2
signs.
to 10. Yeah,
Yeah, it will be
50
5
by
by 2 multiplied by 10. It is like 25 more decimeter cube second inverse. Yeah. So appearance we generally take it as positive, and disappearance we generally take it as negative. You
yeah,
understand?
clear,
All right.
clear, yeah. These are very basics. 2004 I studied.
Yeah. So when we talk about the reaction and when we look into the aspect of this course, we are actually dealing with these. Yeah. Okay. Okay. So now let's move on to our next question. So the reaction between A plus B is first order in A and second order in B. Give the rate equation, rate expression, and then find the units of K, assuming yours. Yeah. This is similar to our first question. So yeah, this is very similar to here. I can write the rate equation like K into concentration of A into concentration of B. So this is the rate equation, and we know how to calculate the units of uh, rate, which is liter by mole to the power n minus 1. I mean, yeah, n minus 1 to the second inverse. So with this, we can calculate the unit also. In this case, let's go on to the next question. Suppose we are having a reaction between P and Q,
So
and
just can you go to that earlier one
yeah,
just for
just a question.
clarification? Yeah, previous question. Okay, so here A and B, then we are first order. Okay, A we have to take it as first order, and B, and okay, accordingly we have to
Okay, okay.
estimate.
Yeah,
Okay,
I'm sorry. So it's the guy just, it's in the first order. So in the second, it is like should be this. Yeah, B is in the second order. So whatever comes as the order, that comes as the superstate.
Correct.
So
Yeah. Okay. Then
this is,
according this will vary. That unit remains same. Correct.
yeah,
Second and yeah, n minus one. Okay, that is correct. Yeah, yeah, yeah. That we already discussed.
yeah. So here also there's like this one. This is very similar. So here, yeah, this is also very similar question. It is in the order of 3 by 2 and P is in the order of minus 1. So this is also very similar question. I think this is easy. Okay, if this is much more tough question where we can see K is given as
Just
5.7
one
into,
second, sir. Can you go back
yeah,
for a moment?
here
Yes.
also,
Okay.
yeah. So if
Yeah.
you better, like it is almost time, that is why I was rushing. So that's so it's
No
easy.
problem. Yeah.
Yeah, it is already, we are having barely half an hour more. So if K is 5.7 into 10 to the power minus 4 mole inverse decimeter cube. Actually, I think that should be, yeah, decimeter cube second inverse. So it is K comes in the reciprocal of R. So that's why we are getting a unit like that. And calculate the reaction, rate of reaction, which is the first order in both A and B, where A and B concentration of A and B are both given. So this is the first question, and similarly we having a second equation. I think this is also equally simpler, but yeah, we can write R as K into A and B, as it is said that both are in the first order. And it is, and we are provided with values of everything. It is 5.7 to the power to 10 to the power minus 4, and this is the unit. And we know A is given as 5.0 into 10 to the power minus 2, and B is given as 2.0 into 10 to the power minus 2. Okay, the units are coming like more. Yeah, we will take care of the whole unit part later. Now let's see this one. And here it is like 5.7 into 5 into 2, so it is basically 10. So it is like 57 into 10 to the power minus 4 minus 4, it's minus 8. And the unit part is like um, mole inverse decimeter cube second inverse multiplied by mole decimeter cube inverse into mole into decimeter cube. So basically we can cancel one mole and we can cancel one decimeter inverse. So basically it is mole by decimeter cube second inverse, and the answer is like 5.7 into 10 to the power minus 7. So that is the answer.
Okay. 10 power minus 8.
So generally we will write like 5.7. So keeping the,
Okay. 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 Got it. Got it. Clear. Okay. Fine.
yeah. And similarly, it is the next question is also very similar. If it had been 5.0 into 10 to the minus 0, so we have reduced the concentration of A, and we have also reduced the concentration of B. What would be it is also very similar. So we here will so here also we'll be having a very similar answer. It is just um, case of multiplication, like R is equal to 5.7 into 10 to the minus 4 multiplied by 5.0 into 10 to the minus 4 multiplied by 2.0 into 10 to the power minus 3. So it is just a game of uh, multiplication. It is like 10 to the power minus 4 minus 7, 10 to the power minus 11. It is like 5.7 into 10 to the power minus 10. Okay, so that is our
Yeah.
part. Yeah,
Yeah.
and the unit remains same as we are not changing the units by, and that will remain definitely same. Okay. Okay, the unit remains same because we are not changing the order of the reaction. The order of the reactions is remaining same for the second. Both the cases are remaining. Both they are both first order.
Yeah. Yeah.
So yeah, this is an equation where we need to see. So we are also talk about batch reactor. So this question comes from on the point of batch reactors. So calculate the time to reduce the number of moles by a factor of 10. So if our initial number of molecules is Na, like Na0, now the molecules number of not molecules, number of moles is actually Na0 by 10. So initially it was Na0, now it is Na0 by 10. The batch reactor. So now currently what is the current reaction, rate of reaction? That's we know K. So if you know the basic equation, then we'll definitely be able to do that. So these kinds of questions are very well. So already the formula is also given. Ra is basically current concentration. We can write it as the current concentration itself. Then we need to
So
move
one
forward.
question we can go with RA, the other means CA will be there, another one will be divided by 10.
Yeah. And there
Oh,
is yeah, there is, it should be kind of exponential decrease or reaction. This is just like problems in nuclear. So we have a
okay.
like calculation of the lifetime in a nuclear reactor. This is very similar to that kind of equation, where the like the moles will be reduced as a function of will decay exponentially. Basically, the number will reduce in an exponential manner. So here it is just like our final concentration. I can like the final concentration. I'm just writing it as half, and be written as the initial concentration multiplied by e raised to minus k into time. T represents the time. Now it is just rearrangement and taking logarithm. So I know final reaction, it is like 0.1. 0.1 of initial concentration is your final concentration. Multiply k by 10 is 0.1. Yeah. Multiplied by is equal to I multiplied by e to the power minus k. The value of k is given 0.046, and it is given in the unit of minutes. So definitely t should also be in minutes. Okay, so I can cancel this thing and I can take a logarithm. And let me, so now it is just mathematical rearrangement. I can write it as 1 by 10 is equal to 1 by e raised to 0.046 multiplied by t, or I can write e raised to 0.046 times t is equal to 10. So 0.046 times t is nothing but ln 10, and then t can be written log 10 by 0.046. That is now just do some numerical, okay? And then we'll get the answer. So answer is around like from around 20 t is like around 20 minutes. We solve this, it will come in that order. Okay, so that's it. It is just we need to know how this equation goes, and everything is just pure mathematics, and this is very fundamental mathematics, so everyone can do. Okay, if this question is clear, then
Is
we'll move.
natural logarithm or the other one? Natural logarithm means it is something coming around 50.
I think it
Long
is
10.
ln itself, right? You will move to ln log 10 itself, right?
Okay, okay. I just used the on-screen calculator. Okay.
Yeah,
Natural logarithm of 10 is 2.3.
yeah,
2.3 divided by 0.046. That is roughly, it is coming around 50.
50. Okay, whatever it is just a matter of some calculation, maybe.
Okay, okay. Just to
Yeah,
confirm.
the
Because,
major crux
yeah,
to know here in this particular thing is we just need to know this equation, and rest
absolutely. Yeah,
is just
yeah,
mathematics.
correct. So final and initial we have to consider and
Yeah,
yeah,
this is the whole
clear. That
idea
is,
of solving such a kind of a problem.
yeah, yeah, clear.
So the main reason for predominance of trans state in a crystalline polyethylene is now. So this was few numericals. Now let's move some on the theory-based question. So what is the main reason for predominance of a trans state in crystalline polyethylene? So it will first option, it will allow better chain packing to produce a denser structure. Each trans state is lower in energy due to steric hindrance effects. All trans conformation is entropically favored. formation of chain folded lamellar requires trend states. So I think this one is discussed in the class itself. So that's why I put this question particularly. So yeah, let's discuss the answer. So the answer is it will allow better packing of the chains, and that better packing means if the denser it gets and denser it gets, the better crystalline it becomes. That is the reason why the trans states in the polyethylene are basically the main reason for its crystalline nature. The next question is rank the structural features of a quenched high molecular weight semi-crystalline polymer in order of their size. Smallest first and then the largest. So which according to the size, what is the order that is possible? The first one is chain length, lamellar thickness, spherulate radius, root mean square, end-to-end distance of chain. Which one is the best answer? If we fix a particular polymer, suppose it can form a spherulate also. Suppose we have a particular, and then we are talking. So in this, which one will have the lowest thickness in the first, and then finally it becomes the largest. Which length scale is higher? So we are just talking about different length scale. Which length scale is the largest length comparing to others? And in the order.
Maybe spherulites depends upon the size. It should be small and followed by lamellar and root mean square distance, and chain length should be the higher. Uh, just a guess because I am not like this root mean square chain distance I am yet to go through because I have completed only the two video lectures
Yeah.
and another 2 days. That's why
Okay. Okay.
I'm not clear sure about it. So, yes.
But the answer is slightly different. So
Okay.
the smallest among this is the lamellar thickness. It
Okay.
basically comes within the spiritual radius itself. So the
Okay.
lamellar
Correct.
thickness
Correct.
is much smaller than the spherulite radius. So it is the
Mm.
smallest. And the next one is this root mean square end-to-end distance of the chain. So we are basically, and then it comes the spherulite radius, but the chain length can actually, chain is actually a folded also. So when we just expand the entire chain length, so that will be actually much larger. So chain length is the largest and followed by the spherulite radius, then followed by the root mean end-to-end chain distance, and finally it's the lambda. So yeah, definitely sir will explain all these parameter in a much better way. This is so we'll be able to understand. So yeah, so it is option A that is correct.
Yeah.
A much a better explanation is also given here. Okay, so yeah, move on to next question. In a PHB, uh, is a naturally occurring biodegradable polymer produced by bacteria which melts around 200 degrees Celsius and form large spherulates readily on cooling. What sort of heat treatment would result in a solid with mechanical property most suitable for making fizzy drinks water? So annealing at a temperature 100 degrees for 1 hour, heating just about 200 degrees until it is melted, followed upon by rapid quench at room temperature. Heating just about 200 degrees until melted, followed by rapid quench to room temperature, and annealing at 100 degrees for 1 hour. Heating to just 200 degrees until melted, followed by slow cooling to room temperature.
Generally, spherulites does require a rapid or slow cooling. Not sure, but
Yes,
it is okay.
yes,
That needs that may be the crux there actually. When
yeah,
how fast we
definitely it basically deals with how rapid it should cool or uh, rapid it should cool or how like yeah it depends on its cooling temperature. cooling or how fast we just cool it down. So this is also a very particular question. So I'll just explain you the answer. So answer is the third one where we have to increase the temperature till 200 degrees so that it gets melt. And as you said, this is spirulate. We need to rapidly cool it to room temperature. And then again to have this kind of application, we will then it annihilate to 100 degrees Celsius afterwards. So this is the answer. So some explanations are also given here. The slow cooling, the major thing is like slow cooling will improve matter. Yeah, explanations also given here. So, state two techniques that we could use to determine the degree of crystallinity in a polymer.
XRD is one,
Yeah,
like salinity we can find.
that yeah, crystallinity definitely we can use exactly. The other thing is basically we can also use this DSC technique also because where we can also get an
Okay,
idea
okay.
about this glass transition temperature also. So that will give us an
Exactly.
idea on how crystalline the material is. So how rubber it becomes, then the more amorphous it gets. So basically it is XRD and DSC.
Yeah.
So compare and contrast the features of crystallization in polymers to that of other types of
Just one
polymers.
second. Sorry for that. Can you please just go back?
Yeah, just a second. DSC and it was DSC and XRD.
Okay, okay, clear. Yeah.
And in this question is like compare. So we have talked about crystallization in polymers. So how it is different from that of materials such as metals and ceramics. How the whole crystalline nature of polymer is different from metals as well as ceramics. So this is a basic differentiation.
Metals, when we say crystallinity, it is having well-defined crystal lattice, like different configurations.
Yes.
Whereas in polymers, it is more we cannot call entire polymer as fully crystalline.
Yes.
Maybe because of their ordering, the level of ordering of the chains, we can call a portion of it is crystalline, like what we discussed, like laminar type, where we have ordered crystallinity,
Uh,
and it will have other semi-crystalline and amorphous portion also.
yes.
Especially, okay, the high order of crystallinity we can see in the LCBs, liquid crystalline polymers, mainly the ceramic type of vector and aramid type of systems.
Yes.
And metal, of course, definitely it is having very well ordered crystal structures.
So that is a major crux also. So if in crystallization of polymers, we basically see that the polymer chains will be arranged in a dense manner. So that is the thing that is causing a crystallinity of polymers. So the basic thing that is causing the crystallinity is the polymer itself. So we can say the monomer itself, like the monomers when they are connected together or if they are stacked in a well concentrated manner, that will act as a crystal. So the basic unit here it's like monomer for that of a polymer. But when it comes to metals and ceramic, there are specific atoms that are arranged in a particular. So the basic unit we can say are atoms for basically metals and ceramics. And here we can say it is like monomers. It is a combination of maybe a combination of even molecules is forming a basic unit. Okay, so yeah, and as you said, the structure and basically we can call polymers as basically it is like semi-crystal, not an entire crystal, but definitely it will have crystalline part as well as it will be having this amorphous parts. So it is kind of a semi-crystalline in nature, and whereas metals and ceramic can be like pure crystals, and also yeah, the crystallinity of polymers can be destroyed much faster when we consider that of metals and ceramic because it is much more prone to this kind of degradations. If we increase the temperature much faster, that also depends on what kind of metals. But we are talking kinds of in a much general manner. So yeah, that is the case. So yeah, so these are the things. The building blocks are long chain molecules for polymers. For metals, they are individual atoms. For ceramic, it can be some kind of compound. In crystalline nature, polymer can be semi-crystalline, amorphous, or mental, and that is a similar case for ceramic also. And for metal, it is a very highly crystalline, well-defined unit cells are present for metals. And crystallization process, it is chain folding and packing in lamellae that is causing the crystalline nature for polymers, whereas atomic arrangement by this metallic bonding will cause crystallinity for metals, whereas ionic or covalent bonding arrangements will be the crystallization process for ceramic materials. The key properties, like, yeah, these are the basic things. Properties like mechanical, optic, those will be maybe similar to many things. And yeah, that's it. The major difference comes from these three. So these three are the major things, and the major thing is the building block itself, and also crystalline energy. So these three are the, when this kind of a question is asked, basically these two are the primary thing, and then it comes the crystallization process itself. Okay, that is, yeah.
Yeah, yeah, yeah.
So that is, I think that is all for today. So yeah, I think I got many questions from. Okay, I forgot to add that particular reference at this time. I can share that particular book where I got many of the questions. I think I forgot to add that in this one. Yeah, so these are general references that can be followed. Thank you. Thank you, sir, for listening.
Yeah, can you just show one more time this reference?
Yeah, just a second, sir. This one is the primarily used textbook. First, I'm sorry.
Yeah, I think this is fine. Yeah, I
Yeah,
have noted that.
yeah, okay. Okay,
Yeah,
sir.
thank you. Thank you very much.
Yeah, thank you so much, sir, for attending. Thank
Thank
you.
you.
Okay, sir,
Shall I
please.
take a leave?
Yeah, sure, sir, please.
Thank you. Good night. Bye.
Okay.